Welcome to the course on power quality. So, we are discussing power quality improvement in permanent synchronous generator based diesel generator sets. The PM diesel based set, we use the distribution static compensator for voltage control and power quality improvement. A diesel engine runs at constant speed and used as a prime mover. These are typically the block diagram of the complete system, where we have a PMSG generator, we have a voltage source converter with the battery on the DC link, and of course, we have a variety of linear load, maybe single phase load or it can be 3 phase load, maybe linear or non-linear. And the very purpose of putting the compensator is that it provides the load balancing, it also provides the voltage regulation and harmonic elimination. Apart from that, it also provides, the battery provides the optimum fuel utilization in the diesel DG set, because the DG set have to be operated between 80 to 100% load. So, if it is load is less than 80%, the battery have to be charged with extra power. However, this battery can give this extra power to have the load more than the capacity of the permanent synchronous generator and DG set. So, that is the benefit, and moreover during dynamic load condition, when you have a inverse current of the motor load, dynamic load, then it can provide, the battery can provide instant energy. Apart from that, the converter can provide the reactive power. So, that your DG set is not overloaded, it is not going to be more than rated power with the rated voltage and rated current. So, then the voltage and frequency are not affected of the DG set, in spite you feed the higher than the rated capacity of the generator like. So, typically we use the ILST control algorithm for this, for single phase load on the 3 phase generator. Of course, we use for 3 phase 3 wire add-along based control algorithm and hyperbolic tangent function based LMS algorithm for 3 phase 3 wire load with the battery energy storage system. That typically this ILST based algorithm, when we have a typically the unbalanced load. So, we have a load current, sense load current here, we extracted the fundamental component of the load here, and by fundamental component here of the all 3 phase current, then using the sample hold and zero crossing detector, we are able to get the you can call it the amplitude of fundamental active component of current, and that we get for all 3 phases. So, we take average, pass on through low pass filter to avoid the noise. So, this is the active component of load current. Similarly, we estimate the reactive power component, fundamental reactive power component and the amplitude of this, and then we use the. So, for the active component, we use the DC link voltage controller. So, we add with this typically with load component. So, that becomes the active component of the generator current multiplied the template, which are in phase with the phase voltage. So, we get the active component of current of the generator. For reactive component of current, we use the terminal voltage regulator, because you have to regulate the voltage also with the help of this to equal to reference voltage. We use the proportional integral control, so that steady state error is 0. These are the typical DC quantity, it work very well. And then we subtract it from load, because load reactive power have to supply locally by DStatCom, only the a small amount of reactive component have to flow through the generator side, and this amplitude we multiplied the quadrature template, which are at 90 degree leading with the voltage. This gives the quadrature component, and then we add both. So, this gives you a reference 3 phase generator current, we have a feedback generator current, and we put current controller for generating the gating pulses like. So, it really regulate the provide the load balancing, harmonic elimination and voltage control at PCC. And these are the line for 3, of course, the Widow based algorithm for again extraction of the fundamental component for all 3 phases reactive component, and then voltage control along with the similar line. So, we get the reactive component and active component, multiplied the template phase template and quadrature template, we get the 2 component, and that give the total net generator current. Then we have a feedback current, and we give this to generating the gating signal for the voltage source converter used in this system. Then we have a hyperbolic tangent function for the with the battery energy storage system, where we have a again extraction of fundamental component for all 3 typically you can call it like active component, similarly for reactive component. So, we have a typically here you can call it the terminal voltage regulation is required for AC side, but for this we can limit typically from the, because we are putting the battery. So, you can use like a typically this load and extra power can go to the typically the battery. So, we get the weight, and finally, we are able to multiply with the template in phase, and this reactive component we multiplied with the template at quadrature template, we get the quadrature component, we add together, and this give us like typically you can call it the generator current and multiply the minus the sense generator current, we get the gating signal. So, these are of course, in different operating conditions we use the 3 different control algorithm and then with the simulation result. So, here you can see there is an increase in single phase load unbalancing is there, and increase in the load, and that is the reason generator current increases, but the compensator is able to compensate for reactive power of the load as well as provide the load balancing. That is the reason you get a balance current on the generator. It also regulates the terminal voltage as well as its a DC link voltage is also regulated. Then this is used for nonlinear load. So, you do not have a on one phase and you have a nonlinear load connected between line to line for other 2 phases, and load is also increased. So, this compensator is providing the load balancing as well as the harmonic elimination. That is the reason you find the current balance current in phase, typically balance current as well as the smooth current even during dynamics, and these are the typically compensator current, and we regulate the terminal voltage as well as we regulate the DC link voltage like. And this is the typically harmonic spectrum of the load current. The total harmonic distortion of load current is 31.5%, where the generator voltage TAD is 2.67% and the generator current TAD is 4.48% like. Now, coming to the performance of PMSG DG set with the 3 phase 3 wire lagging power factor load. This is you can see the lagging power factor load, low load, then load is increased, then unbalanced load is realized. All the conditions are realized, but you can see the generator current are balanced, sinusoidal, and terminal voltage is also regulated to constant value. Like at where even a varying load also, and DC link voltage also regulated and frequency also regulated like. Then this is subjected to nonlinear 3 phase nonlinear load. You can see here 3 phase nonlinear load, lower value and then increased load, then 1 phase load is removed. So, load balancing, harmonic elimination and change of load is applied to this system, but you can call it the generator current are balanced, sinusoidal, and all the compensation is providing harmonic elimination, load balancing. Apart from it regulating the terminal voltage also to constant value, with the DC link voltage also regulated. And the TAD of load current is 24.33%, is 3 phase nonlinear load, and the generator current TAD 4.78, where you are getting the voltage TAD 2.91% like. So, it is able to improve the power quality typically when that. And now, typically we can call it, this is with the battery system. Like here we are putting that you should generate either if load is less than 80%, so you should generate minimum 80%, if load is more than 100%, you should generate 100%, and here also load is increased. So, here 80% generation is there, and load is increased, is only that much it is generating, and when load unbalance is created, then certainly again the power of the load is lesser than 80%. So, again it generates 80%, but load balancing and reactive power compensation provided for the load, and you are able to have a balance current between 80 to 100% all the time, like not below 80%, and this is the you can see when load unbalancing there, you will find the second typically harmonics in the battery current, like which is going into the battery, but voltage is regulated and frequency is also regulated, as well as DC link voltage is also regulated like. Then you have a nonlinear load on this system. So, initially low nonlinear load, then nonlinear load is increased, then load unbalancing is there, but generator current remains between 80 to 100%. If load is less, and the compensator is providing load balancing and as well as harmonic elimination in this case, and that is the reason generator current remain balanced and sinusoidal. And voltage is also regulated, and you can see the battery accordingly getting charged and discharged depending upon the load condition. So, here battery is getting with the clean, you have a very less linear load, then it has a 6th harmonic because you have a 3 phase nonlinear load, and second harmonics in the battery current when you have a single phase nonlinear load. That is automatically comes in nature of the system, and this is the TAD of the load current 20.44, where the TAD of grid generator current is 3.46 and generator voltage TAD 2.56% like. These are the typical experimental result. You can clearly see the load generator currents are balanced sinusoidal, where the load is unbalanced, there is no load on one line, and typically even your source current also balanced like. This is again in case of nonlinear unbalanced case load, but generator current are balanced, and TAD of the voltage is only 2.8%, where your generator current TAD 4.7% also with this nonlinear load. And then during the dynamics, like if nonlinear load is increased, still you will find the generator currents are not getting disturbed, they remain constant, and DC link voltage is also regulated during dynamics also, and then with the lagging power factor load also it works very well for correction of typically the power factor of the load and providing compensation. This with the nonlinear load, but generator current are balanced and sinusoidal, and compensator is providing the compensation. So, voltage TAD 3.6%, where your generator current TAD 3.9%, where the load TAD of this is 20.5% like or so. And during dynamics, when load is unbalanced, but generator currents are not disturbed, they remain sinusoidal and balanced, and the battery getting charged or discharged when you remove the according to the load. And these are typically like you can think about, I mean we are having even a generation typically fixed, but even the load may be little more than that, it is capable of feeding that condition also at varying load also. I mean like you can see typically, I mean you are having more power than that. So, you can generate more or less, but the battery will get automatically charged from that like or compensation. And this is you can say when load is increased, you will not find any change in the generator current, and when you have a load is off, again generator current are not affected, because the charging and discharging of the battery take place, as you can see the battery current here. Even if you have a dynamic load, you have ingress current, but generator current are not affected, neither generator voltage, generator current are not affected, and you have a motor load which comes from the compensator current, like battery is able to provide the current momentarily. You can see the battery current, it provides the energy very instantly, so that there is a ingress current of the load is taken care by this, and you are not having any change either typically of the your generator current or generator voltage, like, and DC link voltage remain there. And now we are coming for 3-phase 4-wire system by providing force lag, so that neutral current is also compensated either with the unbalanced load or with your non-linear load. Neutral current is always there in 3-phase 4-wire system. This is the typical control we are using here, notch filter, adaptive notch filter, for extracting the fundamental here, and we are getting the total out 3 phases. Then we take average, we have a DC link voltage control, and we are able to have in phase with that, so compensator current corresponds to that. So, the initially lagging power factor load, I mean you have a typically a lagging power factor, no load, then lagging power factor and balanced load, but the generator current are balanced and sinusoidal, and compensator is providing compensation. Thermal voltage is also regulated, neutral current compensation is also provided here, and DC link voltage is also regulated. Then you have a non-linear load, balanced non-linear, but neutral current is compensated by the fourth leg of the compensator, and you are providing the here virtually the harmonic elimination, load balancing, neutral current compensation and voltage regulation. All those features are put from the STATCOM. So, you can have this voltage is also regulated by in this PMSG, and you have a total harmonic distortion of the load current around 37.76, where the generator current TAD 3.63 and the your terminal voltage TAD 2.29% like. And you can see the here the with the unbalanced current also, unbalanced load also, you are able to have a balanced generator current with the neutral current almost negligible, and compensator providing that compensation like. And you have a non-linear load, still we are able to get balanced load, and you can see compensator current to compensate that, and neutral current is almost negligible, where the your compensator and load neutral current are compensated by each other. So, we have a TAD of voltage 3.6%, and where the generator current TAD 3%, where the load current TAD 38.5%, like under such a highly non-linear load, it is capable of compensating, and having a very low TAD of the terminal voltage of the generator as well as the generator current like. So, here the typically kind of non-linear load and unbalancing, but generator current are balanced and sinusoidal, and neutral current compensation also taken care, and neutral current of the generator is made 0 like. Now, coming to the power quality improvement in synchronous reluctance based DG set, this machine has come very recently, a new machine, very interesting machine, because efficiency of this machine is typically of better than induction generator, and it has again all the features of your synchronous machine, and it is a brushless like. So, synchronous reluctance machines have been used for motoring purpose in limited number of applications. The machine has its potential and explode in standalone power generation. It can be used as a generator similar to an induction generator with and without capacitor bank, and this STATCOM is used for voltage control and power quality improvement, and diesel engine runs at typically constant speed prime mover like. This is the typical case when we have a battery along with the typically a voltage source converter, and we have a typically here 3-phase non-linear load. So, battery provides the power leveling along with the voltage regulation here, and even during dynamic load also it can, and we can operate at this DG set on what we call it like optimum fuel utilization. So, that the generator is not loaded less than 80%, not more than 100%. If consumer load is more than 100%, battery provides the power through converter, and if load is less than 50%, battery charges like. Even during dynamic load also, this converter and battery is capable of giving extra power more than 100% of the generator, but we are not taking the power more than 100% from the generator. So, generator voltage current and power are not affected by dynamics of the load converter takes, because it is a fast provide the fast dynamic. Like we have used here the synchronous reference frame theory for one typical case of single phase load, and power balance theory for 3 phase 3 wire load, and your instant symmetrical component theory for 3 phase 4 wire with battery, and of course, composite observer with the 3 phase 4 wire load, and these are typically for SRF theory. So, we have a DC link voltage control here with the help of PI controller, and we have a typically load fundamental component extraction, and then we have a terminal voltage regulation also, because in this case also we have to regulate the terminal voltage, because we do not have any exciter system. So, only the compensator provide the reactive power for regulating the voltage, but this is the compensating reactive minus the load, we get the generator reactive component. Here we get the active component, which comes certainly only from generator for loss of the converter as well as the load, and from this we transform this dq into the 3 phase with the help of inverse spark transformation. So, we get a reference 3 phase current. So, we have a sense current of the generator, and then we have getting signal generation power. This is typically power balance theory, which is used certainly in the same way as the DC link voltage control, and then AC voltage controller. So, we get the quadrature component, we get the direct access component from which we add to the load, and here we subtract from the load, and we transform again back to the, and then we have a 3 phase reference current with the feedback current we give the gating signal like. And this is symmetrical component theory, where we are able to have a DC terminal voltage control, here reference terminal voltage, and this is the terminal voltage. We get the typically an angle which is responsible for regulating the voltage by the active power, and here we have active power. So, we get the reference generator current, we have a feedback generator current, and we get the gating signal like. So, coming to the performance, I mean this is typically the first case when we have a single phase load, third phase there is no load, and load is increased, but the you can call it the generator current remains balance and channel. Since battery is there, so generator current varies from 80 to 100%, also not more than that, and the compensator is providing the entire compensation, load balancing and power factor correction of the load, and terminal voltage is regulated, and DC link typically and frequency is also regulated of the system. Then we have a on this system non-linear load, lower load, but the generator current and power is not less than 80%, and here we have a non-linear load. So, we provide the harmonic analysis as well as load balancing and voltage regulation. So, all those features are demonstrated here, and terminal voltage regulated here, and frequency is also regulated. Now, coming to typically here 3 phase linear, I mean you will find again generator currents are not much changing, whether load unbalancing is demonstrated as well as voltage. Typically your you can call it the reactive power of the reactive load is all demonstrated with the load balancing, but voltage is regulated, I mean terminal voltage regulated, frequency is also regulated. Now, coming with the non-linear load, I mean you have a balanced non-linear load, very less load, increased load, and then load unbalancing, but compensator is providing voltage regulation, load balancing and harmonic elimination. So, that generator current remain balanced and sinusoidal. And this the typically harmonic spectrum of load current is 24.44%, total harmonic distortion where generator current is 4.13%, and the terminal voltage TAD is only 0.19% like. And this is the case typically we are having a battery operated. So, here we are putting now the optimum utilization of the generator from 80 to 100%, and there is a small load. So, battery getting charged, when load is increased battery is not getting charged, floating between 80 to 100%, and when you have a unbalanced load, the battery getting charged, but with the second harmonic into the battery because of load unbalancing. It regulates the voltage, it provides the power leveling, it eliminates the typically negative sequence current as well as it supplies the reactive power of the load. Now, coming with the non-linear load, like then of course, its battery getting charged, when load is increased battery is not charged, and then when load unbalancing the battery getting charged, but second harmonic is there in the battery. Voltage is regulated as well as the generator current is regulated between 80 to 100% all the time for fuel, I mean optimum fuel efficiency zone to operate the generator in all the time. And this is the TAD of load current 20.6%, where the your you can call it the source current is 4.22%, and where the generator current TAD 1.16 and the voltage TAD 0.14%. These are the experimental results with unbalanced load, I mean like line to line load, but generator current are balanced and they are 80 to 100% in between, or this is typically the unbalanced non-linear load, but the generator current are balanced, and the TAD of load is 30.9%, where the generator current is 4.5 and voltage is only 1.6% or so. In the case when we are reducing the load, I mean like here, but the generator current, I mean not much change here, and it provided the harmonic compensation, load balancing and voltage regulation also. And these are typical case of your, you can see the generator current and reactive load, and varying typically linear load and non-linear load. We are able to have a load harmonic compensation and voltage regulation, and TAD of voltage is 1.8%, where the load generator current TAD 3 and load TAD typically of this around 24.4%. And dynamics, when typically apply the load on one phase, other two phase already working. So you do not find major, there is increase, but the load, your generator current are balanced and sinusoidal. It is not affecting the generator, and your compensator is providing active filtering when non-linear load is applied. And you can clearly see the typically the sinusoidal waveform at operating at unity power factor at typically under different operating conditions like and this is the case when your typically load is reduced, and the generator current is still balanced and sinusoidal, and accordingly battery gets charged or discharged. Like, so generator is not affected, which operates 80 to 100% of the load, and then the motor is starting. Dynamic load, it compensator takes care, and generator and neither generator voltage or generator currents are affected. Certainly battery instantaneously give the active power for inverse current of the motor as a part of the load, and DC link remain regulated. This is another algorithm for 3-phase 4-wire composite observer. So, we extracting fundamental current, active and reactive current, and then we are having a DC link voltage control with the addition of load current, both supplied by the generator. Here we have voltage regulator at the point of common coupling minus the load active component that give the reactive component which have to flow into the generator. So, the amplitude multiply the quadrature template, which are 90 degree leading than the voltage. We get the reference quadrature component of current, and we get active component of current multiplying the amplitude multiply the phase template of the voltage. So, both we add, we get the total generator reference current. We sense the generator current, and as well as neutral current reference is 0. So, that also we, and we give the gating signal for 4 lag converter, and that is typically the circuit for providing the load balancing, neutral current elimination, voltage regulation in this system. Like, so, coming to typically you can think about first there is no load. So, battery getting charged, and if there is a typically addition of the load is there, then the generator current balance, but when load unbalancing is there, the generator current still remain the balance and compensator providing the voltage regulation, load balancing. And coming to typically non-linear load, of course, there is no load. So, that time battery get, and when you have a linear load, balance non-linear load, balanced load, but compensator is working as a active filter. When unbalanced load, non-linear, so it is providing compensation, neutral current compensation also, as well as it providing voltage regulation. So, all features are included here, and the TAD of the load current is 37.76%, where the TAD of your generator current is 3.60% and terminal voltage TAD 2.29%. This is the experimental result that neutral current is almost eliminated on generator side, and generator current are balanced, where the load is unbalanced, and you have a neutral current also, because even linear load. This is non-linear load, generator currents are balanced and sinusoidal, and you have a terminal voltage TAD 1.6%, where the TAD of your generator current is 2.9%. This is source current TAD, and this is the TAD of load current 36.6% like. And this is typically you can call it, the one phase load is removed. So, power reduced and neutral current changes, and but the neutral compensation point, so source neutral current is 0 and providing compensation and all like. Now, coming to the numerical problems. So, a 415/75 kVA synchronous machine based isolated diesel generator set is integrated with the 660 volt battery through voltage source converter. This DG system control in such a way load on the remain always between 80 to 100% of the generator capacity to improve the efficiency of the DG set. If the load is below 80%, the battery charging take place. If the load is beyond 100%, discharging of battery take place, and the in between 80 to 100%, the battery remains in floating, and there is a load shedding provision. If load increases above 125%, calculate the watt hour rating of the current and battery. The peak load of 120 backup 4 hour is desired. So, this is the typical system with the battery backup, and we have a load. And coming to the solution, given that isolated 3-phase 3-wire 415 volt 75 kVA diesel generator set based synchronous generator is connected to 660 volt battery with the DC link of the voltage source converter, watt hour rating of the battery fully backup 4 hour with the desired percentage. So, this is we can calculate the battery energy with the 4 hour of capacity with the typically of 25. So, it comes 75 kilowatt hours, and the battery current we can find out from energy divided by voltage and hours. So, we get 28.41 ampere in the battery. Coming to second example, a 400 volt 50 kVA permanent synchronous generator based isolated diesel generator set system is integrated with 720 volt battery through a voltage source inverter, and the DG set is controlled such that the load on the system remains always between 80 to 100% of the generator capacity to improve the efficiency of DG set. If the load is below 80%, the battery charging take place, and if the load is 100 beyond 100, discharging take place, and the in battery 80 to 100% load, the battery remains in floating condition. Calculate the apparent power flow through VSI power factor 0.8 linear load with 50% of generator capacity of 50 kilowatt, 85 generator capacity or 110% of generator capacity. This is the typical system with the battery which provide the power leveling. And coming to the solution, this given the isolated 3 phase 3 wire 450 and 50 kVA DG set is based permanent synchronous generator is connected to 720 volt battery at the DC side, and the active power of the load is 50% of the capacity, that is 25 kilowatt, and the power factor is typically 0.8. So, reactive power of the load is 18.75, and the active power of the DG set 80% capacity. So, that is a 40 kilowatt, and the active power of VSI we can calculate from DG minus the load. So, it comes 15 kilowatt, and the reactive power of the VSI is 18.75. So, VA apparent rating under P square Q square, it comes 24.01 kVA, and that at the another condition the active power of the load is 85%, that comes like a typically 42.5 kilowatt, and reactive power of the load comes from this 30.87 kilowatt, and active power from the DG set 85% capacity, that is 42.5 kilowatt, and the active power through VSI thus is 0. So, the reactive power from the compensator is 31. So, rating is also of apparent rating of K, your VSI is 31.87 kVR. Now, coming to third situation when the load is at 110%. So, it is 50 into this 55 kilowatt, reactive power is of this is 41.25, and the active power of the capacity is 50 kilowatt. So, the VSI have to give from the battery around typically 5 kilowatt, battery get discharged, and reactive power of the VSI is 41.25. So, total P square Q square is a 41.55 kVA. Now, coming to third numerical problem, a 3 phase 400 volt 22 kilowatt 50 hertz self actuated induction generator machine is used as a DG generator for diesel generation, needs excitation of 9 kVR at no load and 15 kVR unity power factor full load. Self supporting pendulum VSI is used for meeting the reactive power requirement of this induction generator. Considering the fixed capacitor rating equal to no load kVR, calculate the reactive power flow and the line current of VSI at no load at unity power factor load of full load 22 kilowatt, 0.8 lagging power factor 20 kilowatt, 0.9 leading reactive power load. So, this is the typical system. We have a load power factor varying and load power varying with the VSI operating STATCOM. So, given that a 3 phase self actuated generator 400 volt 22 kilowatt 50 hertz squirrel cage induction generator based DG set needs the excitation of the 9 kVR at no load and 15 kVR at unity power factor load. So, fixed capacitor of kVR is now here taken 9 kVR. At no load the reactive power flow through VSI is typically 0 because 9 kVR is needed, and line current of VSI will be 0. And for unity power factor load of 22 kilowatt, so reactive power load of the typically required for reactive power for load is typically here is the full load minus the your capacitor. So, that is 6 kVR, and the line current will be of VSI will be your IC equal to Q1. So, it will be 8.66, and the now for lagging 0.8 lagging power factor load full load 20. So, it is a reactive power of load is 10.65, and we can find out VSI QFI from full load requirement, load reactive power and capacitor. So, 15 plus 6 10.65 minus 9, so it becomes 16.65, and current we can find out in compensator is a typically from kVR. So, it comes 24.04 ampere like, and for 0.8 leading power factor the reactive power of the load is typically of 10 kVR from the power factor and the kilowatt rating, and reactive power total of the VSI will be your Q load minus QC. So, all are is minus. So, here it is leading 4.65 kVR, and negative sign denotes that the have to provide lagging reactive power to maintain power, and line current of VSI we can calculate from QSI root 3. So, it comes 6.71 ampere. So, now coming to in the question problem 4 solution. In the previous question, if the fixed capacitor bank is used for reducing the rating of the VSI and VSI is used only for the smooth control of voltage at rated value, then calculate the kVR rating of the and line current of VSI, a unity power factor 22 kilowatt, 0.9 lagging power factor and C 0.8 leading power factor full load. is the typical system, and if the reduced rating VSI is what is calculated you as the VSI work in leading and lagging power mode depending upon the extent of load, its rating can be reduced at appropriate AC capacitor. So, induction generator available to cover the load range. In the most of the cases, half the required rating other than no load can be selected based on the rating of VSI, and full load reactive power rating is selected as per the rating of AC capacitor. So, at no load the VSI work as an inductor, and at full load it work as a capacitor. So, for unity power factor load of 22 kilowatt, the kVR rating of this STATCOM is QFL minus this. So, it is 15 minus 9 by 2, 3 kVR. So, capacitor rating is now Q0 plus QFL minus Q by 2. So, it comes like a 9 plus 3, 12 kVR. So, at no load VSI is providing 3 kVR lagging reactive power. At full load, it provides 3 kVR leading reactive power to diesel generator set, and line current of typically comes your 3000 divided by root 3 400, it becomes 4.33 ampere like. And for 0.8 lagging power factor load of 22 kilowatt, the reactive power of the load is 10.65 kVR, and kVR rating of VSI is typically calculated. So, 8.325 kVR, and the line current of this typically of Q upon root 3 VSI. So, it comes 12.02. For 0.8 leading power factor at a full load, so reactive power of the load is 10.65 K, and the kVR rating of the VSI full load plus load reactive power minus Q by 2. So, it is also minus. So, it is a 2.375 kVR leading, and the line current of VSI is calculated from this. So, it comes typically 3.35 ampere. So, with this we like to summarize the power quality improvement in DG set. So, we discuss conventional synchronous generator based DG set. So, harmonics of the source voltage or generator voltage and the current should be kept within the limit of IEEE 5/9 standard under highly nonlinear load, and power factor of the source has been maintained at unity by voltage source converter operating under different conditions, and the unity power factor operation has been able to reduce the derating of the conventional synchronous generator DG set. Now, coming to self-actuated induction generator based DG set, there has been a slightly variation in the frequency of the supply with the load due to changing of the slip in the self-actuated induction generator. The main challenge in this generator is to variation in frequency with variation of load due to variation in slip. In case of permanent synchronous generator based DG set, the frequency of supply could be maintained 50% with slight variation of plus minus 0.4 with the help of variable frequency drive and used as a prototype, and it has been observed that the PMSG based set DG set give the very smaller variation in the supply frequency and the terminal voltage under different loading conditions as compared to conventional synchronous as CIG and synchronous generator set. Coming to synchronous reluctance generator set, it gives the very small variation in supply frequency under different loads unlike SCIG, and the variation in terminal voltage is also small, and the main disadvantage of this generator is that it requires a heavy excitation current as compared to self-actuated. So, the size of the generator is larger among the conventional synchronous generators, self-actuated and PMSG of same rating. These are the some of the references which we referred for typically for the power quality improvement of DG set, and typically for different generators and different, and thank you.